In this screencast, I will discuss a few problems from our classwork sheet in the topic of friction. And as usual, when we are discussing classwork problems as screencasts, I want you to take detailed notes in your classwork notebook at the appropriate place. So we start with the extra classwork problem number 10. In this problem, there is a uniform rod AB and the length of that rod is given to be L. This rod is kept inclined at an angle theta with the floor as shown. So end A rests against the wall and similarly end B, it rests on the floor. The wall is smooth, which means that there is no friction at end A, and at the same time the floor is given to be rough, and the coefficient of friction between the floor and the rod is given to be mu. Now your intuition will probably tell you that if you keep the ladder at a smaller angle of inclination, that is, you decrease the value of theta, you go on decreasing it, finally a stage will come when the ladder will slip. That is, the lower end of the ladder will slip towards the right, and simultaneously the upper end of the ladder will slip down. In other words, there must be some minimum value of theta. There must be some minimum value of theta below which the ladder will lose equilibrium. And that's exactly what we have to find in the question, the minimum value of theta for retaining static equilibrium. So to do this, we draw the FBD of the ladder under these limiting equilibrium conditions. I've been calling it a ladder. It's actually given to be a rod, so I'll just call it a rod henceforth. We need the FBD of the rod in these limiting equilibrium conditions. Now the rod is given to be uniform, and therefore the weight acts at the midpoint of the rod. Weight is going to act here. So I've assumed the weight to be W. It acts at the midpoint of the ladder, and you have the length now is split into two halves exactly, L by 2 on this side and another L by 2 on this side. The other forces acting on the ladder, on the rod, are at end A, the force exerted by the wall at end A. Now since the end A is resting on the smooth wall, the force exerted by the wall on end A of the rod must be a normal reaction only, since friction is absent. So that normal reaction, I'll call it NA. And finally we go to the lower end of the ladder, of the rod. Now the that end is resting on the floor. So let me first draw one of the forces which can be present. It's the normal reaction exerted by the floor on the rod at end B, so I call it NB. And you also know that this particular rod is on the verge of slipping, so end B is on the verge of slipping towards the right. There is impending slipping in the rightward direction, which will mean that there is limiting friction at end B exerted by the floor, and that must be in the leftward direction. And since it is limiting friction, I'm going to write it as mu times NB. So this is the complete FBD of the rod under limiting equilibrium conditions, and we are now going to use our force equations and our moment equations to figure out what is the minimum value of theta for equilibrium. Now one may wonder, where in this FBD have I used the fact, or have I used the data given in the question, that theta is minimum. I've used it over here. When we say that the friction is equal to the limiting friction, it means that the object at that point is about to slip. It's on the verge of slipping, and that means, of course, that theta is going to be minimum, because we know that when theta decreases beyond a certain extent, the slipping actually takes place. So the equality of the frictional force, when we say that the frictional force equals the limiting friction, automatically we are minimizing the value of theta for static equilibrium. Now let's try to find all these forces, and on the way maybe we can figure out what is the value of theta. So the first equation we'll use is sigma Fy is equal to 0. So the forces in the vertical direction, they must balance, and there are only two forces in the vertical direction. One of them is the weight vertically downward, the other is the normal reaction NB at the lower end. So naturally, for these forces to balance, NB must be equal to W, and when this happens, mu NB is naturally equal to mu times W. So I have reduced the number of unknowns in the FBD. I have got rid of NB and replaced it by W in two different places. Now the next unknown is NA, and perhaps if we find NA, we will be able to figure out the value of theta. The forces in the x direction, that is in the horizontal direction, also balance. In other words, sigma Fx is equal to 0. And there are only two forces in the horizontal direction, NA, which is rightwards, and mu W, which is leftwards, and for them to balance, obviously NA must equal mu times W. So what I'll do is I'll just get rid of this mu times NB. I'll just write it as mu W, and I'll also write this as mu W over here, so the figure looks a bit simple. And likewise, instead of saying NB, I'll just write W over here, get rid of this NB is equal to W. So this is the FBD of the rod under limiting equilibrium conditions, and we want to find what is the value of theta. Now theta is not going to figure in the sigma Fx. It hasn't figured in the sigma Fx equation, nor has it figured, or nor has it appeared in the sigma Fy equation. Now we can get it in the moment equation, because, for example, if you consider the moment of this force mu times W about the end point B, about this point, then the moment is going to be the force, which is mu W, the magnitude, multiplied by this distance, and this distance is going to be L times sine of theta. So theta is going to figure in some of the moment equations. So let's try to write an appropriate moment equation for this particular rod in limiting equilibrium. In fact, I'll do just what I said right now. I'll take the moment, the total moment sigma the total moment about endpoint B. So sigma MB, we know it's equal to 0 for equilibrium, and there are only two forces which have a non-zero moment about B. One of them is this weight, and the second one is mu W. This mu W and this W, they do not have any moment about B, for the simple reason that they pass through B. So we won't consider these two forces in the left hand side of this equation. So we'll first consider the force mu W. Now the moment of this force about B is in the clockwise direction. You see it's trying to turn the ladder in this direction about B. and by our convention, well, we can change the convention, but in this particular problem we'll take anticlockwise as positive. That's our usual convention. Of course we can change it in certain problems, it doesn't matter. So we'll take the anticlockwise direction as positive, and then I get a negative moment by mu w. It's minus mu times w, that's the force, and I multiply the magnitude of the force by the perpendicular distance between the line of action of the force, which that line I drew from the point B. So this is nothing but L sine theta. It's the same L sine theta I've written over here. So I have to multiply this by L times sine theta. So once again, mu w is the magnitude of the force and L sine theta is the perpendicular distance, and this minus sign we have attached because we know that the moment in this case is clockwise, and our convention in this problem is anticlockwise is positive. So that's the moment due to the first force. Now let's consider the second force, this weight W, which has a non-zero moment about B. You can see that this force tries to turn the rod in the anticlockwise direction about B, and so its moment must be positive. So I write a plus sign, then I write the magnitude of the force, which is W, and then I multiply the magnitude of the force by the perpendicular distance between the line of action of the force and point B, in other words this distance, and this distance can be easily found by considering this right angled triangle whose hypotenuse is L by 2. So naturally this distance is L by 2 multiplied by cos theta, which I multiply over here, L by 2 multiplied by cos of theta, and this is of course equal to 0, and some things cancel, W cancels, L cancels, I get a 1 here, I get half cos theta equals sine theta, and there's a mu also. Where is it? The mu should be over here, multiplied by mu, and I get tan theta is equal to 1 upon 2 mu, which means that theta is tan inverse of 1 upon 2 mu. So this is the minimum value of theta corresponding to the static equilibrium of this rod. Now there are 2 points to notice here. The first is, somebody may object and say that there is a value of theta which is smaller than tan inverse of 1 upon 2 mu, for which the rod will definitely be in static equilibrium, and that is the minimum value of theta. So the value of theta which this person is talking about is theta equal to 0. Imagine theta being equal to 0, it would mean that the rod is horizontal. So I just keep the rod horizontal against the ground like this. So this is the ground, the wall is over here maybe. Definitely it is going to be in static equilibrium, there can be no argument about that. But we have disregarded this particular case in this problem for 2 reasons. Firstly, it seems to be a trivial solution. Just reading the problem, it is pretty clear that given the situation, the rod is definitely, it will be in static equilibrium for theta equal to 0. So we are assuming that the problem doesn't want us to find this trivial solution. In fact, we have assumed that the value of theta which is asked corresponds to a situation where point B is the only point of contact of the ladder of the rod with the ground, and similarly point A is the unique point of contact of the rod with the wall. There are only 2 points of contact between the rod and the floor and the wall. So that's our assumption, and under that assumption, of course, this particular trivial solution cannot be accepted simply because there are so many points of contact between the rod and the floor. In fact, if we assume this second diagram which I have drawn, the FBD which we have drawn earlier is not valid. For example, if I look at this normal reaction W from the floor, it will no longer act at point B over here. It will simply be over here at the midpoint of the rod, and it will exactly balance the weight of the rod, which also acts at the midpoint. So because the FBD itself is different, we did not get theta equal to 0 in our answer over here. So that's the second reason, of course, why we are neglecting this particular case, is that the FBD is no longer valid. And of course, if you go deeper into that, we have drawn the FBD for a case where there are only 2 points of contact between the wall and the floor, and that's the assumption that we are making. So we need exactly 2 points of contact, and that's our assumption when we are solving this particular question. Now there is another thing to note, very interesting in this question. We got a value of theta min as tan inverse of 1 by 2 mu. Now just imagine a scenario, an experiment in which the floor, it becomes rougher and rougher. So you conduct this experiment in which you find the value of theta min on successively rougher floors. Now our intuition tells us that when the floor becomes rough, the ladder can be put at an inclination which is even smaller than in the previous experiment, because slipping becomes more and more difficult when the floor becomes rough. So in the next experiment, when the floor becomes even rougher, maybe the rod can go that way. I've been calling this particular rod, I've been calling it a ladder sometimes and a rod sometimes, so I don't know why, but just I hope you understand what I'm saying. Anyway, as the floor becomes rougher and rougher, the value of theta minimum goes on decreasing. This is from our intuition, and even if you go by the mathematics, you see that as mu increases, see, the floor becomes rough means mu is going to increase. So this particular positive number goes on decreasing, and naturally theta min, which is tan inverse of a positive number, so it's a first quadrant angle, and the angle itself is going to decrease as this particular quantity goes on decreasing. So the mathematics seems to correspond to the intuitive feeling that we have based on our experience. So that finishes question number 10. The next question we will attempt is extra classwork question number 11, and this question is related to the previous question which we just did. The question states the following: we have to prove that in the previous problem, so you can see that I have drawn the same rod AB inclined at some angle theta with the horizontal. So prove that in that case static equilibrium is not possible if the conditions are reversed. That is, if the floor was smooth and the wall was rough. So this is the exact opposite of what we did, the conditions given in question number 10, where the floor was rough and the wall was smooth. So assuming that the rod cannot get any friction from the bottom, from the floor, because it is smooth, but it can get friction from the rough wall. So even if it can get friction from the rough wall, we have to prove that static equilibrium is impossible. That is, the rod cannot remain stationary for a long period of time. We have to prove this. Now we will use the method of indirect proof, in which we will first assume static equilibrium to exist, and then we will end up with some contradiction. So assume this rod is in static equilibrium, and of course the forces and the moments must balance in that case. So let me draw the forces, let me draw the FBD of the rod. So at the midpoint of this uniform rod you have the weight acting, W. These two lengths are L/2 each, and we have normal reactions. We can have, it's not compulsory, but there can be a normal reaction. It can be 0, but there is no harm in showing it. So there is NB here, and we can show an NA here. Remember, normal reaction is a push, not a pull. And further, we can't have friction over here because the floor is smooth, but there is a possibility that there is friction over here, and of course the friction is going to prevent the end A from sliding in the downward direction. So the friction must be, first of all, it must be static friction because we have assumed static equilibrium, and secondly the friction must be in the upward direction. So I'll just draw that force here. Frictional force at A acting on the rod is F. I do not know whether it is limiting friction or whether it is comfortable static friction, so I can just write a general label Fs. So remember that the condition satisfied by Fs is Fs must necessarily be less than or equal to mu, which is the coefficient of static friction. Let's assume mu multiplied by the normal reaction at that point is Na. Now we have this FBD. No other force can act on this rod. The rod is assumed to be in static equilibrium. So let's try to analyze the forces, and we can even try to find them, and finally we will probably reach some sort of contradiction. So firstly we will use the condition that sigma fx must be equal to 0 for static equilibrium. Now if you look at the rod, you see that there is only one force which is acting in the horizontal direction, and no other force acts horizontally. No other force even has a horizontal component. The other forces are simply vertical. And if the value of sigma fx must be equal to 0, it follows therefore that Na, the only horizontal force in the diagram, and noting that no other force has a horizontal component too, so Na must be equal to 0, and we will of course put that value of Na in the FBD. But before that you must realize that once Na becomes numerically equal to 0, there is one more force in the FBD which will vanish, and that's going to be Fs, because the magnitude of Fs is less than or equal to mu times Na. Na is 0, and when the magnitude is less than or equal to 0, there's only one possibility: Fs is equal to 0. So in the FBD, what I'll do is I'll rub out two forces, Na because it's equal to 0, and Fs also has to go, it's equal to 0. So that's how the FBD gets modified. Now the next thing we can do is to try to find the value of NB. That seems to be an unknown currently, and therefore I apply my next force equation, sigma Fy is equal to 0 for static equilibrium. Now there are only two forces left, and both of them are in the vertical direction. So naturally what I get is the upward force, which is NB, must equal the downward force, which is W in magnitude, and so this FBD is going to get further modified. In place of NB, I write its value, which is W. So I have reached a stage where I can no longer apply any force equation. I've already utilized sigma Fx and sigma Fy equal to 0, and the FBD has got quite simplified. There are two forces, each of magnitude W. One of them acts at the midpoint of the rod, the other one acts at one of the end points of the rod. And now we will search for a contradiction. The third condition which must be satisfied for static equilibrium is that the total moment about any point must be equal to 0. That must necessarily be satisfied if static equilibrium exists. Now you can easily see that this is not the case in the current state of the FBD. That is, if I find the moment about B, let's say, then this force has no moment because it passes through B, and this one will have a non-zero moment. The other way to visualize it is these two forces form a couple, a non-zero couple, and therefore the moment about any point is equal to that non-zero couple. So this particular condition is not satisfied by the remaining forces. Of course it will be satisfied if and only if W is equal to 0 and W is equal to 0, both of them. But we are assuming that the rod has some weight, that this will be a trivial solution, so we will not consider that sort of solution. I end with a contradiction, which therefore means that somewhere I've gone wrong in my initial assumption, namely the assumption of static equilibrium. So under the given conditions, it is not possible for the rod to be under static equilibrium. That is how you solve this question.